So in the last class, I was discussing about designing the state feedback control system, which we have designed using a pole placement technique. That means if we have a system x dot is equal to ax plus bu, then the state feedback control gain is nothing but ui replaced by feeding back the states, all the states. So u is equal to minus kx is the state feedback controller equations, and k is the state feedback controller gain. We have also used mainly two methods. One is the Bhaskara method, and second one is the Ackermann's formula to find out the controller gain, state feedback controller gain. So today what I will do is I will just show you, use an example to show you its implementation, the state feedback controller gain, its implementation, so that it will be clear to you. Okay. And also when we have designed the state feedback controller earlier in the last class, we have not considered the reference trajectory. That means is basically is stabilizing the states only. It's not tracking the set point of a process. So we all, if time permits, then I will also go for the set point tracking problem only. But today's class mainly I will devote to the some kind of sort of tutorial of developing this control strategy using MATLAB and Simulink environment. Okay, so let me first share my what I will share desktop. I think I have to share the desktop, otherwise. Okay, so can you see the slides? One of you please respond.
Yes, sir.
Okay. So what we'll do, we'll take one example. This is a benchmark example used by everybody. In fact, the control system design is being taught by not only by chemical engineer, electrical engineer, electronics engineer, mechanical engineer. So many people are there in all disciplines. Basically, the control systems are required. So this is an interesting problem which is used as a benchmark problem. You will find in many references in of this problem. So we'll take this problem here, inverted pendulum on a cart. So here basically, let me take the other point. Here basically on a cart we have got an inverted pendulum. So pendulum one end is connected, pivoted over here, and this is the bob. So this basically moves. Control objective is to put this when the cart is moving. When the cart is moving, the control objective is to put this pendulum in this position, right? So the pendulum bob will be here, so that alpha will be 0. Okay, so the angle will be 0 when we move the cart. So in this case, I'm not developing the mathematical model over here. Hello, please mute your mic. Everybody. Hello. Okay. So the mathematical. Hello. Uh, so the mathematical equations for this, which I am not developing over here, it is available in all the books, you refer the book of Ogata, you refer the book of any control system design, you will get this benchmark problem and this mathematical equations. So the mathematical equations over here is given as this. This is x double dot, that means d2x by dt square. This small m is the weight of this link as well as the mass of this bob over here, and the capital M is the mass of the card. Alpha is the angle over here, L is the length, and X is the distance. So the two equations we have, one is d2x by dt square is equal to this equation, another is d2 alpha by dt square is another equation. So we have got two equations which describes these systems. Our objective over here to find out a controller equations so that I will move the card such a fashion so that this will always stay in this position. This will always stay in this position. Okay, so that is our control objective. Now to do that, from these dynamic equations, we have to develop the state space model. From this dynamic equation, we have to develop the state space model. Now, when we are developing the state space model, we also think that initially at steady state, this is at this position, and the alpha, this angle alpha is very small. So if this angle alpha is very small, then we can say sine alpha is equal to alpha and cos alpha equals to 1. Okay. If this alpha is pretty small, then we say the sine alpha is equal to alpha and cos alpha is equal to 1. If you do that, then this equation, because the nonlinearity in this equation is because of this sine alpha and cos alpha terms. So if you do that, then this nonlinearity will be reduced. Moreover, we also say this alpha dot and x dot, alpha dot and x dot are very small. Alpha dot and x dot are very small. So that alpha dot and x dot, I take this as 0. Okay. So these are basically assumptions we are considering to linearize the model. So if you do that, so for small alpha, cos alpha is equal to 1 and sin alpha is equal to alpha. And you also assume alpha dot and x dot will be kept small, so it is, this value is taken as 0. Now from these equations, then in that case, from these equations, we'll have x double dot is equal to u minus m mg by m alpha. Okay, x double dot is equal to this. Here basically you can see this will become 0. This will be mg alpha, and this one m plus m sine square alpha I can write as 1 minus cos square alpha, and cos alpha is equal to 1. So this will become 0. Clear? So then in that case, I will have x double dot is equal to u by m minus mg by m alpha. Similarly, alpha double dot also I will write in this form after doing these simplifications. Now these equations are linear equations. Now to devise the state space model, we assume that Z is a state variables. That means Z1, Z2, Z3, Z4 are the state variables. And this Z1 I say is X, Z2 I say X dot, Z3 I assume equals to alpha, and Z4 is alpha dot. So then I can write the, once I assume that, then I can write the state equations as Z1 dot equals to x dot is equal to z2. Z2 dot will be x double dot will be minus mg m z3 plus u by m. Similarly, z3 dot will be alpha dot equals to z4, and z4 dot will be alpha double dot will be m plus m by ml gz3 minus u by ml. Okay. Now this is basically now z is equal to az plus bu term. Okay. This is now a z is equal to az plus bu term. So if it is a z is equal to z dot is equal to az plus bu term, then a's are, if I consider m is equal to these values, the a's will be given by these expressions. 0, 1, 0, 0, 0, 0 minus mg by m 0 and so on. Elements of A will be given by this, and elements of B will be given by this. Okay, 1 by m and minus 1 by ml. If I consider mass of the cart as 0.45 kg, mass of the bob is 0.21 kg, L is 0.305 and G is 9.8, then I will have this A is over here and B is this value. C over here, we are basically measuring x and theta. So C will be this one, this one will be 1, and theta will be 1, Cx will be theta, and D will be 0, 0. Okay. So this basically gives you the state space model. This basically gives you the state space model of the inverted pendulum. So this is a linear state space model. We have first have the nonlinear dynamic equations, and then we made certain assumptions. We made certain assumptions to linearize around the nominal steady state values. The nominal steady state value is the position where alpha is equal to 0. So the nominal steady state values and x is equal to 0, and then we devise these equations. Okay. Now once we have the state space model, then we can do a MATLAB implementations. So rather than writing over here this MATLAB implementation here, let us go to the MATLAB environment itself. Let us go to the MATLAB environment itself and we'll do the MATLAB implementation, and then we'll go for a simulink implementation. Okay. So let me go to the MATLAB environment. Can you see the MATLAB workspace? Hello?
Yes, sir.
Okay.
Yes, sir.
So the first few lines, basically I'm copying from here. It basically defines the state space model. So we have the state space model over here. We have the state space model here where I define the A. I first define the M, the capital M, small m, length, and G, the values, and then I define the A, B, C, and D. So we'll have A will be given by these values, B will be given by these values, C will be this, and D will be this value. So a state space model is defined. Now the next step is, if I have to implement the state feedback controller, then first thing we have to check is the whether it is controllable or not. So we have to check the controllability. So we form a controllability matrix. So let's say CB is the controllability matrix. We form equation is B, A into B, and A square into B, then A cube into B. Okay, so this will give me a controllability matrix. What is the mistake over here I have done? B A B A square B and so CB matrix is this one. So I got the CB matrix. So I put the first bracket, it will be third bracket. So I got the CB matrix over here. Just hold on just a second. Let me take my space. Yeah. Sorry for the interruption. So we have created the controllability matrix. Now we'll see the rank of the controllability matrix. So using the rank command in a MATLAB. So if I put rank CB, then the rank is given by 4, which is the number of states in the system, which ensures that the system is controllable, which ensures the system is controllable. Now let us see for the open loop system, where the pole lies. So that we can find out if we find out the eigenvalues of the A matrix. So EIG is the command for the eigenvalues. So I use this command P is equal to eigenvalues A. Here we can see one of the pole is lying on the right hand plane. We can see that one of the pole is lying on the right hand plane. So this is basically an unstable steady state. The steady state what we have taken is an unstable steady state. So slight change in the initial condition, will move away that system from this unstable steady state. Okay. So the next thing is we have to design the controller. So before doing that, let us see. I will take this one. We'll define the system. Okay, so this is the open loop system. Now if I give an initial condition, so say x0 I will give 0, x dot will be 0, theta I will give a slight change in the theta. So I will give 0.1 radian and this one will be 0. Okay. So now I change the initial conditions, right? Initial condition, I see what is the response of this open loop system. You can see over here the response for this initial condition. This is completely unstable system. So slight change in the initial condition, the system may systems run away. Basically, it has become an unstable system, right? So our objective, the first step is that we design the feedback controller to stabilize the system. Okay, so to design that controller, we have to have a reference trajectory because the poles over here, one of the poles are lying on the right hand plane. So the first thing is we pull back all the poles on the left hand plane. So we take some arbitrary values, let's say some arbitrary values of mu1, mu2. So I will take mu1, this one is mu1, mu2, mu3, mu4, where all poles are basically lying on the left hand plane. All poles are lying on the left hand plane. Okay. Now, in MATLAB, we have got two commands for finding out we can do by writing the program for finding out the gain, which is pretty simple. We can use the Ackermann's formula, or we can use the Passgrove formula to calculate that. We can use the Passgrove formula to calculate that. So instead of doing that, in MATLAB we have got two commands, which one is the command place, which uses the Passgrove formula. Another command is the Acker, which uses the Ackermann's formula. Okay, so the two commands are there. One is place, another is the Acker. So the two formulas are there. One for the Passgrove formula, another for the Ackermann's formula. So instead of writing the code for the Passgrove formula or Ackermann's formula, we will use the MATLAB implementation of this technique. So we'll find out the gain K will be given as place, and it requires the A matrix, B matrix, and the desired location of the poles. So here basically mu is the desired location of the poles. Okay, so if I do that, then I will get the gains of the state feedback controller gain. Now I get the state feedback controller gain. Now once I get the state feedback controller gain, then I can find the closed loop state space model. The closed loop state space model here basically will be A will be changing. So A will be A minus B into K. Others will be remaining same. So here basically I'm copying this. So I have got AC, BC, CC, and DC, which are basically the closed loop state space model. Now so let us now build the closed loop state space model, right? So I'll say CCL is equal to SS. I'll take AC, BC, CC, and DC. Now I have built this closed loop model. Now again I will check this initial. Here basically I have used the open loop. Now I use the closed loop with the same initial condition. Now you can see the system can be stabilized by that controller. Now the closed loop system is stable. So because of the changes in the initial condition, the theta basically I've started from 0.1, the changes from the initial condition, the controller puts that system into the desired steady state, Okay. And here basically the important thing is the response over here. So this is basically there a slight overshoot over here, and this is the response of the thing. So this by changing the desired pole location, you can customize the responses over here. So you can change the desired pole location, find out the responses and so on. Okay. So this is basically gives you an idea how the state feedback controller is designed. Now what I will do is this simulation is based on the state space model, linear state space model. Now the question is whatever controller gain we have designed from the linear state space model, whether that will work on the actual system. So that we can find out if we go to the Simulink environment. Okay. So now we have the gain. So the K is this value. We have the gain. Now what we'll do is we'll go to the Simulink environment. So let me go to the Simulink environment. So I have already designed pendulum for the class. Okay. So in the Simulink, this one is the nonlinear dynamic equations for the pendulum. So here basically if you look at the system, this is the U. Here the actual equations are here. So dx dot dt, this is d2x by dt square equals to that. This term is over here, and this is also d2 theta by dt square. So double derivative term for x and double derivative term for theta is given over here, and then these terms are integrated. This is the first integration, this is the second integration, this is the first and second integration. And the states are basically you have got x dot, theta and theta dot. And the input is the u over here. Okay. So this is basically the pendulum, and I put some restriction on the u. This is plus minus 10. I put a constant, so the u value cannot go beyond plus minus 10. Okay. Now, to implement the state feedback controller gain, I have to first take all these signals. So these signals I can mark it. So I have got 4 inputs over here. Okay. So I connect the 4 signals to a single signal, and these signals now will go to a gain. So I'll take a gain element. So this I am getting by doing a double clicking over here, and then I search for a gain element. So I'll get the gain element over here. I put this one is as K. Okay. This gain element also I say this is basically a matrix multiplication, matrix K into U. Okay. Then we also further do this thing as I select this and I make it a subsystem. Okay, I make it a subsystem and then I create a mux for this subsystem. Here basically I say this is a state feedback controller. Okay, so this is a state feedback controller and the parameter basically is the K. Here will be SFC gain and the parameter values will be I default I give 0, 0, 0, 0, then I apply. Okay. This one, let me flip that. So I flip the block and I connect this and this one will go back to the process. This one will go back to the process. So what I will do over here is I will take one summation block over here and take this one as take a constant block over here. This will be necessary later on. So in the beginning itself, I am connecting and I am connecting over here this block. Okay. Now the SFC, this gain now I can take from my MATLAB environment. So this is the values of the gain I have calculated. Okay. So here we copy that gain and I put it the values of the gain over here. I put the values of the gain over here. Okay. So I'll go to this environment. Now this u is equal to minus kx. So I multiplied k into x. This u will be minus, so it will be minus, and then I add these two terms. Here basically this is 0, so this one will have no effect on this. So this will go directly over here. Okay. Now let's say, let me run this to see whether there. Before that, let me put something over here. Let me put also some scope over here. So I will take over here is the dashboard scope. I will take over here is the dashboard and I'll connect the signals over here. So I'll connect this signal and this signal. So these two signals I have connected. Now if I run it, what will happen? So this is in a 0 position. Okay, this is in a 0 position. Now we'll check if by changing the initial conditions, what will happen. So in changing the initial conditions means for the theta over here, if I click on this integration block, the initial condition over here by default is 0. So I take this initial condition, some value of 0.2, let's say, and apply. Okay. So I change the initial condition over here and then I rerun. Now you can see I have changed the initial conditions and the responses are like this, but it goes to the 0 value. It goes to it can stabilize the system. The nonlinear, now here the system is a nonlinear system, the actual system. We have designed the controller based on the linear state space model of this system, and then we are implementing this controller on a nonlinear system, this controller on a nonlinear system. So if and we can see the values like this. We see the system is getting stabilized, the theta angle is getting 0, the system is getting stabilized. So this one, basically the X, which slightly varies and then stays over here. Okay. Now, so this also let us change this thing. The initial condition will also take an initial over here. We'll change the initial condition for the X also. So we'll change initial condition also in the X. So now we change the initial condition for both X and theta. Let us see whether it can stabilize the system or not. Okay. Now let us run this. You can see over here, even then also it can stabilize the system. So internally the controller again can stabilize the system over here. Okay. The next step is basically here basically we are not giving any set point. The set point over here is 0. We are not giving any set point over here. Okay. Now our objective is to also move the X, that means move the card. Our objective is to move the card at the same time that theta will be 0. So that inverted pendulum will stay its desired position. It stay vertically, right? So what we can do is we'll first change this one to the original values. So we'll change to 0. Here also we'll change to 0. And then we'll try to give a set point change. So the X will vary. Okay. So if the X will vary, then what we can do is we'll delete this term, we put this one over here, and then we use another summation block. Will be minus plus. So X signal So the feedback of X will come over here and set point will be come over here and this will be joined over here, but before that there will be some gain element. Gain, let's say this will be, I put this one as 1. So I put some gain element. This one I bring it down. I bring it down this one. Okay. So this is the system now. So here now what we are doing is I am giving feedback of X so that I can give a set point. So I can give a set point over here. I give a gain element over here. And then I will check whether this system can track also the set point, the movement of the X. Now here this gain will be negative. So this will be, let's say, I'll take a very small value, let's say 0.4 or 0.2 even. And this position, let's say, I stay 0.5. Okay. Now let us run the system and see what happens. Now here you can see in this case, I have given 0.5 as the set point. The cart will be moving here, but the cart goes here up to some values of 0.12 or 0.13, 125 or so. It goes to that position, although the theta, that pendulum is keeping straight. So in this case, in this formulation, it is not possible to put to track the set point. In this formulation, it's not possible to track the set point. But what we can do is we have used the gain over here, so I can increase the gain value. Let's say I increase the gain value to 0.8. What will happen? So I will increase the gain value 0.8. So your oscillation will start, but it goes nearer to the 0.5 value. But here oscillation will start. Okay. So obviously we require some theoretical knowledge to establish the set point tracking for this system also. Okay, some theoretical knowledge for set point tracking of this system also. Okay, so let us, is it clear to you? Then I will move forward to the next section. One of you please respond.
Sir, can you show the SFBC ones?
Huh? Which one?
The SFBC block.
SFBC block. Okay. This SFBC block is nothing but a gain.
Okay.
Huh?
Okay, sir.
And in the gain element, with this by default it will, if you take the gain element, by default it will be element wise multiplication. But in our case, it's basically matrix wise multiplication. So we'll take the matrix wise and there we. And then this gain block, basically I use a subsystem. Over here in the diagram, you get a subsystem and automatically this will come. And then you can edit them. You can edit marks. You can create marks and then you can edit marks. Okay.
Yes, sir.
In a similar fashion, this was created. In fact, this model I have taken from the MATLAB itself. But these are pretty simple. You can create yourself.
Yes, sir.
Okay. So once you have this thing, now you have the result of this thing, SFBC controller. Now in the Simulink model, we established that whatever the controller gain we have obtained using the linear state space model, that will also apply on the nonlinear state space model. Okay. So let me save this one, and now let me go back to the I'll go back to that state feedback controller. Then I have got another this thing, servo situation. So let me now design of the state feedback controller for the servo situation. So what we have seen over there, that although we can stabilize the system using the state feedback controller, but we cannot track the set point. Okay, so what we have to do in that case? So just let me go back. So in that case, what we have done is basically this is the system over here, AX plus BU, and this is the state feedback controller gain over here. Now we have implemented up to this KI, and then we have given a set point. Now here also you have to give an integral action over here. You have to give an integral action over here, then it will integral action over here, then it will reach to the set point. You have to give an integral action over here, then it will reach a set point. Okay, so with that we can do it in our system. But also, what will be the values of the KI? We know how the K is designed, how to get the K values, that we know already, but how to get this KI values. So from this block diagram, we can write the equations as x dot is equal to ax plus bu, y is equal to cx, u is equal to minus kx plus k1 xi. So this one, this error, k1 zeta, this is error. So k1 into zeta. So u is equal to minus kx plus ki into zeta. And zeta dot is r minus y. This r is the set point. Zeta dot is r minus y is the zeta dot from this block diagram. So this is basically from this block diagram, we'll get this equation, zeta dot is equal to r minus y is equal to r minus cx. Now I add these two equations, x dot is equal to ax plus by, bu, and zeta dot is equal to r minus cx. If I do that, then we'll have x dot t, zeta dot t will be a0 minus c0 xt zeta t, b0 ut 0 1 rt. Okay. Now in this state space equation, I have got the input rt, input u as well as r. Input u as well as r. Okay. Now at steady state, this zeta dot t is equal to 0. So y infinity will be equals to the r. Okay. So x infinity, xi infinity, that means at steady state will be given by these expressions. Now if I subtract this steady state with this dynamic equation, then what will happen? So if I subtract this, then x dot t minus x dot infinity, zeta dot t minus zeta dot infinity, I will get this expression. So I'll get these expressions. Okay. The r term over here will cancel out because r is a constant term. So r infinity equals to r. So this will be cancel out. So I will have these equations. Now we define xt minus x infinity is equal to xct, zeta t minus zeta infinity is zeta et, and ut minus u infinity is ut. If I define that, then in terms of new variables x, zeta e, and ue, I will get these equations. And ue, I will get kxet, ki zeta et. Okay. Now I define et as xet and zeta et is the new variable et. So this will be has n plus 1 vector. So this one are basically I take on this as error vector. These are basically nothing but the error. So we'll take this as an error vector. And if I take this one as an error vector, then this equation will become E dot is equal to A hat E plus B hat UE. Okay. Where A hat and B hat will be given by these expressions. Now this equation with UE over here, this UE will be K into error. This UE will also become K hat into error, where K hat will be K and minus K. Okay. Now if I implement UE is equal to minus Ke over here, K hat E over here, then E dot will be A hat minus B hat K hat E. Okay. So you get the similar kind of expressions which we have done earlier. So I select the desired eigenvalues mu1, mu2, mu(n) plus 1 of the matrix A minus Bk, and then I A hat, B hat, K hat, and then I find out the controller gain and the integral gain Ki from using a Bhaskara method or a Acker's formula. Okay, so here basically if you have to take the servo situation or set point tracking problem, then the A matrix has to be replaced. A matrix has to be replaced by this one A0 minus C0. B matrix has to be replaced by B and 0. And then using this A hat and B hat, we find out the K gain state feedback controller gain K as well as the integral gain for the servo situation. Okay, so this is basically the technique for taking into consideration of the integral control. Is it clear to you? Okay. So in this system, that means here basically we have to put one integral term over here to get the set point tracking. And but also using that methodology, we will not only get this one, also we will get the integral, this gain also. We can get this gain also. I hope this is clear to you. Is there anything? Is there anything else I have to discuss for this class? One of you please respond. If you do not have anything to say, then I will end the meeting. So what I will do is I will share this Simulink file. I will share this Simulink file so that you yourself now design the controllers for the not only for the state feedback controller gain as well as the integral gain or the KI and implement that so that it will do a set point tracking. Okay. So next week is basically is your it's a break over there. I think some 1 week break is given. Is it so? It's okay. So the next week there will be no class. So the next two classes will not be there. Next week there will be no class because of the break given by New York academic calendar. And what about the assignment? So one of you please respond. What happens to the assignment? I think.
Sir, I think I was trying with the assignment, but it's taking a lot of time. Means I am not being able to properly incorporate all of the things. Little things because I don't know Simulink, so little bit of things is taking a lot of time to investigate. And I could. And in the problem, it seems so many things because it's a multiple input, multiple output. Now I do not really recognize. You have already given us the CSTR model also. That's a standard BCSTR model that MATLAB incorporates. But because of the fact that it's a multiple input, multiple output system, and because individually you have also given us the disturbance and means the relationship between the inputs and the output. So I do not understand why do we at all need the CSTR model. We can scrap, because I tried that way only. I scrapped the CSTR which you have given as a model, and I tried to just enter into the subsystem, which is the model, the equations you have given. So it's taking a lot of time. I really do not understand how do we. So can we get some extra?
Okay. Let me tell you this thing. So that do not go into the subsystem. Then it will be you will have a problem. Let that be a CSTR dynamic model where I have given 4 inputs are there. Out of these 4 inputs, only the jacket flow rate or coolant flow rate QC, I think it's there. QC is the manipulated variable. Others are disturbances, right? And
yes,
your
sir.
output is the reactor temperature. Output is the reactor temperature.
Yes, sir. Yes, sir.
So you take so you have to design a controller, a PID controller using this input and output. So you have got a single output and single input system. Others will remain same. Then you based on that you see what happens. And for other inputs, you like what I have done over here. You use a constant block. Put this constant block as 0 and add to those inputs. So there will be no changes in the other inputs, except in the manipulated variable.
Yes, sir, but while we are doing the cascade control, we need the disturbances and we need this multiple input, multiple output strategy working over there, right?
For the cascade system, you need only the measurement. So for the cascade system, the cascade is jacket reactor temperature to the jacket temperature cascade. So the reactor temperature, you take measurement, you put a controller, the output will go to the set point to the jacket temperature controller. and the jacket temperature controller will take the measurement from the jacket temperature, and the output jacket temperature controller output will go to the your as input to the QC, that is the jacket flow rate. Try yourself. I think this is not easy. This is not a difficult thing. Anyway, you try to submit whatever you want to do. But by hand also you can find out what will be the controller gain and everything. That also you can find out.
Okay, sir. Yes, sir. I'm trying, but that's it. Yeah.
Okay, fine. I will give you in one class. I will discuss this solution also. No problem.
Thank you, sir.
Okay, I am ending the meeting. If there is no other question, I am ending the meeting. So the next week there will be no class. Thank you.
Thank you, sir.